is joined with Davide Barilari, Ugo Briskin, and Yanela Canasa. And all the results which I'm going to talk about are included in a preprint which has been available on the archive since the end of April this year. And it's also going to be published in the Annals de l'Institut Henri Poincaré. And despite this being a probability journal, the work is still fairly geometrical. So please don't be put off by the fact that the talk starts with the title Stochastic Processes. I'm fully aware that I'm talking to an audience which is like mostly in geometry. So that's also what I'm going to try to target at. So I'll keep the stochastic side as light as I possibly can. And for most of the times when we're getting close to stochastic processes, we're actually going to talk about second order partial differential operators on manifolds. So to start off with what our setting is concretely, we start off with a three-dimensional smooth manifold M, and then we equip this manifold with a contact structure. So D is a two-dimensional, or it's a rank 2 distribution, which is given as the kernel of a non-degenerate one form on M. And then MD is a contact manifold, which we additionally equip with a smooth fiber inner product, which lives on the distribution D. So it's not a metric on the full tangent bundle. It's simply only defined on this rank 2 distribution D. And just to justify one word of the title, this now turns DG into a sub-Riemannian structure on M. But for the purpose of the talk, it's perfectly fine if you just think of MD as a contact manifold equipped with like a smooth fiber inner product on the distribution. So what we've set up so far is this typical image where we have a family of planes which is set up in a way that it's completely non-integrable. Meaning if you start at some point in your three-dimensional space and you walk along curves such that the tangent space to that curve lies in the plane of the distribution, then you can go from any point to any other point. So that's our overall setting. And then we are going to put an orientable surface inside this manifold M. And we'll be interested in constructing second order partial differential operators and eventually stochastic processes on that surface. And one thing I'm going to say now while I have this image available is, so notice that if you now put this surface inside this three-dimensional space, then if you fix a point on your surface and look at the tangent plane to the surface at that point. Now there are two things which can happen. Either this tangent plane coincides with the plane given by your distribution at that point, or they intersect in a one-dimensional space. So basically this structure induces you with a line foliation on this surface S. And this is also called the characteristic foliation. And that's something we're going to encounter over and over again as we go along. But this is important. It arises from how your tangent space to the surface intersects the distribution plane. Okay, so this is the setting we actually care about. But now, mostly for notational convenience, we tweak our setting slightly. And what we're actually going to work with is M is still our three-dimensional smooth manifold, but now we assume that there exist two global vector fields on M, x1 and x2, such that x1, x2, and the commutator bracket formed by x1 and x2, that these vector fields are linearly independent everywhere. And what we then want to look at is we let D be the distribution spanned by x1 and x2. You can show that with this condition that x1, x2, and their bracket is linearly independent everywhere, and that D is indeed a contact structure. And we let G be the fiber inner product, which is uniquely defined by requiring this frame x1, x2 to be an orthonormal frame. This uniquely defines you this smooth fiber inner product. And one thing I want to stress, you may now notice that we now implicitly assume that our contact distribution is trivializable because we have those global vector fields x1 and x2. But because throughout we are only concerned with local behaviors, that's not going to be an issue. It's not like restricting our the classes we can look at significantly. It's really just for notational convenience. And once we have those vector fields x1 and x2, we can also consider or define a vector field x0, which is given as follows. So form the commutator bracket of x1 and x2, mod out everything which lies in the distribution, and then what you're left with, we call the vector field x0. And in fact, you can show that x0 is nothing but the Reeb vector field if you consider the contact form omega, which defines this contact structure D, which is normalized such that d omega restricted to the distribution D equals minus the volume form generated by the fiber inner product G. And the reason why I put this in red is that all this works sort of at the intersection of contact and sub-Riemannian geometry. There is a bit of like, it's not very consistent what sign you choose. So it's perfectly possible that you'll read other works where this normalization is just that this differential equals the volume form of G, and then that flips a lot of signs. But for us, it turned out to be more convenient to put the minus sign in here because then it saved us a lot of minus signs later on. So, but yeah, just be aware that it can be that this convention is differently across different works. Okay. And then the last thing we do is we assume that our embedded surface S is simply given as the zero set of a C2 function on M, such that the differential is non-zero everywhere. And the thing to take away from this slide is we now have our global vector fields x1 and x2. We use them to define this Reeb vector field x0, and we have this surface given as the zero set of a function. And one thing I had alluded to earlier is we need to look at what happens when we consider the tangent space to our surface S compared to the distribution plane. And it turns out that the points where they coincide are not necessarily nice, and they cause a lot of problems. And they are called the characteristic points of the surface S. And they can be, you can check that they're given as the points where both x1 of u and x2 of u vanish. And you'll notice, because this is given as like the zero set of functions, this set gamma of S of all characteristic points is, it's a closed set of S. So if we to look at S minus the characteristic points, this is still a perfectly defined surface. And that's what we are going to look at throughout. So we want to construct our limiting operator delta zero on this surface S minus its characteristic points, because I said those are the points where annoying things happen, so we simply take them out. And now, how do we define this delta zero operator? So what we do is we remember we had our global vector fields x1 and x2, and we can construct a global vector field x0. And because by construction they're linearly independent everywhere, we, for each epsilon positive, can induce the three-dimensional manifold M with a Riemannian metric by which is defined by requiring x1, x2, and square root of epsilon x0 to be a global orthonormal frame. And this uniquely defines you a Riemannian metric on M. And once we have that Riemannian metric on M, we can restrict that metric to the surface S. That's all now just Riemannian geometry. And this gives you a family of Riemannian manifolds S, G, epsilon, where S is always our surface. And for this, we actually can take the full surface with its characteristic points. And then we have this metric G epsilon, which varies. And because these S, G epsilons are perfectly well-defined Riemannian manifolds, we can look at the associated Laplace spectrometry operators delta epsilon. And then what we can show is that for each function f, which is C2 and compactly supported away from the characteristic points, we know that A, the Laplace Beltrami operators applied to such a function f, they do converge uniformly on this, like away from the characteristic points. And we don't only know that they do converge uniformly, we can also describe this delta 0 operator fairly explicitly. So the way we do that, it's given as the square of one vector field plus a function b times that vector field. And now what are these things? So x's hat is given as that. If you see it for the first time, it might look very strange to you, but the nice thing about that is that, so early on I claimed that everything we do only depends on MD, the contact distribution in G, and that we only use this x1, x2, and u for notational conveniences. And this is a good place which illustrates that, because in fact, what happens here is that x's hat, it's a unit length vector field on as take away its characteristic points, which points along. So if your tangent space to the surface and your distribution plane intersect in a linear subspace, which they do away from the characteristic points, then this vector field points along this one-dimensional subspace in your tangent space. So in a way, it's a unit length vector field which points along this line foliation, this characteristic foliation induced on the surface S through this contact distribution D. And then you simply need to have a consistent choice of sign. But you can describe that geometrically. And I'll have a picture later on, and it points along your foliation. And then there's also function b defined, which you can also make sense of just by looking at the geometry, but I'm not going to go into the details of that. So this is our unit length vector field, which is also called the characteristic vector field. And then this is the function b. And one thing I want to stress before we go to the stochastic processes side is that this vector field and this function, they actually appear in another scenario. So if you go back and look at those Riemannian manifolds SG epsilon, which we used earlier on, then for all of those surfaces or two-dimensional Riemannian manifolds, you can compute the Gaussian curvature K epsilon. And if you now take the limit as epsilon tends to 0 of those K epsilons, then this is given as this characteristic minus this characteristic vector field applied to the function b minus b squared. And in a way, you can think of this K0 as a notion of intrinsic Gaussian curvature for the surface S in the setting we care about. Because even though it's like originally given as the limit of sort of Riemannian approximations, eventually you do characterize it as quantities which you can define by simply looking at the contact distribution in the surface itself, so where you don't need this Riemannian approximation. And also, moreover, sort of interestingly, is that if you look at this expression, it pretty much characterizes K0 with a Riccati-like equation. So that's, again, very close to what we know from Riemannian geometry. And this is just a side result that this vector field and this function just reappear in that setting again. Okay, but now for the rest of the talk, we're going to be concerned with this delta 0. And just to get a better feeling of this whole scenario, we look at a paraboloid in the Heisenberg group. So what happens if you put this paraboloid in the Heisenberg group? You have exactly one characteristic point, which is at the origin. And then your characteristic foliation or line foliation, it's going to consist of spirals moving upwards. And you can even look at the degenerate case where a equals 0, then you simply get a plane with rays going out of the origin. Okay, and what you can then do is you can change coordinates in such a way that your s coordinates, well, your psi coordinate picks one of the spirals. That's why it ranges between 0 and 2 pi. And then your s coordinate is essentially arc length along one such spiral. And what you then can compute is that your characteristic vector field is simply given as d by ds in that set of coordinates. And this function b is given as 2 over s. That's fairly straightforward computation if you put everything together, which means that our operator delta 0 is given of this form. Now, what I haven't told you yet is how all of this is related to stochastic processes. But what happens is that there's a notion where you can take a second order partial differential operator and let this be a generator for a stochastic process on that manifold. So for instance, if you look at the usual Laplace spectrometry operators on Riemannian manifolds, they are related to a notion which is called Brownian motion, where you can simply think of like a particle diffusing around on that manifold. So it's going to be confined to that manifold and it diffuses around. But one subtlety to be aware of is that the generator of Brownian motion is not the Laplace spectrometry operator, but it's 1/2 of the Laplace spectrometry operator. And because our delta 0 arose as the limit of the Laplace spectrometry operators on those Riemannian approximations, it's natural to now look at 1/2 of this operator. And this is what we end up with. And basically what happens, I'm going to say a bit more about this later, but this is a stochastic process which is going to be confined to those spirals. And interestingly, so if you look at the geometry, it can only ever move along spirals. And you can think, okay, the only way it could change from one spiral to another is through this characteristic point. But right at the end of the talk, I'm going to give a very brief idea that in fact, your particle, which like starts on one such spiral, it's never going to reach this characteristic point if you let this be the generator of the dynamics of this particle. So what happens is that these are really processes which are induced of a particle sort of like it starts on a fixed spiral and then forever it's going to sort of diffuse around on this fixed spiral, and it can never reach this characteristic point, which would be its only way of changing to another spiral. Okay, and just keep that operator in mind. We're going to see it again in a few slides. So it's 1/2 of d squared by ds squared plus 1 over s d by ds. Then another example, and I'm simply including it because it has a nice picture. So if you look at a sphere in the Heisenberg group, and now play exactly the same game again, you end up with 2 characteristic points, sort of the north and the south pole. And now your characteristic foliation is given as so-called Loxodromes, connecting the north and the south pole. And you can also compute 1/2 of this delta 0, but this time around it doesn't look as nicely. But what is important to notice is we have a cotangent appearing here. And what is annoying is this sort of d theta by the s, because theta is given as like an elliptic integral of the second kind in terms of s, and there things get messy. But it did so it served as a motivation for us that this cotangent was appearing here, and I'll tell you in a second why. Okay, so this is like sort of some intuition of how this geometry looks like and how this induced characteristic foliation looks like. And now I want to say a bit more about the stochastic processes. So remember, this was the operator we encountered 2 slides ago when you look at the paraboloid in the Heisenberg group. And essentially, if you now look at this in terms of a one-dimensional process, this is a so-called Bessel process of order 3. And this exactly has this property I mentioned, that if you start a Bessel process on the positive real line, it's never going to hit the origin. And so this basically one case where it appears, it's just take a horizontal plane in the Heisenberg group. Now, a similar process is the so-called Legendre process. And this is very close to the process which we obtained by looking at the sphere in the Heisenberg group. The only thing is it now doesn't have this annoying Jacobian factor. So this now has just a pure cotangent. You can choose k to be any positive number. And this is a process which is confined to an interval 0 to pi over k. And it now again has the nice property, it's never going to hit either of your endpoints. It's going to be confined in this forever. So if that sort of similar transfers to the sphere in the Heisenberg group, what happens is, again, your process is never going to hit the characteristic points. So it's going to be confined to a spiral forever, to one of those Loxodromes forever. The reason why I'm including this in here is, so basically once we looked at the sphere and the Heisenberg group, we were like, well, can we come up with an example where we really can obtain this Legendre process? And we realized, so what we need is we need a sphere inside some 3D contact structure such that the characteristic foliation really consists of great circles, because this annoying Jacobian factor arose by this having this twisted Loxodromes. And the nice thing is, you can simply take a sphere in SU2. If you take a sphere in SU2, you can check that your characteristic foliation is really going to consist of great circles. And then you do indeed obtain this Legendre process. And if you now sort of notice that a sphere in SU2 is pretty much, again, a horizontal plane in SU2, then it's not hard to try and think about, well, what happens if I now take a sort of horizontal-like plane in SL2R? And if you do that correctly, you in fact obtain a hyperbolic Bessel process of order 3. And these 3 processes are sort of canonical processes appearing in stochastic analysis, and they're all linked to the so-called Brownian motion in a particular way. But it's very nice that in a way these 3 processes can be recovered by looking at the Heisenberg group, SU2 and SL2R, which is sort of canonical examples for 3D contact structures. Okay, and to close off, I want to say a bit more about this accessibility of the characteristic points, because I said that if you look at the paraboloid or at the sphere, your stochastic process is never going to hit those characteristic points. So the question is, can we say something general about that? And we can. And for that, we characterize our characteristic points in terms of this Hessian. So it's also called the horizontal Hessian, because we only use the vector fields x1 and x2 to define it. And now this terminology is going to be mildly confusing to you if anyone comes from dynamical systems, but anyone who comes from contact geometry should be more familiar with that. So you have characteristic points, then we generally call characteristic points where the determinant of the Hessian is non-zero. We call them non-degenerate characteristic points, and then we distinguish non-degenerate characteristic points as elliptic and hyperbolic, where elliptic means that the determinant of the Hessian is not only non-zero, but in fact positive. And hyperbolic is that the determinant of the Hessian is negative. And especially the word hyperbolic has a different meaning in dynamical systems, so watch out for that. But we use that where elliptic and hyperbolic mean positive and negative. And we can further show that if we now take this delta 0, look at the stochastic process with 1/2 of this operator as its generator, because that's the canonical thing you look at, then all elliptic characteristic points are inaccessible, meaning the stochastic process can never reach those points, like it didn't reach them for the paraboloid and the sphere. And hyperbolic characteristic points, they can be accessed, but in fact, there are only like 2 characteristic lines going through this hyperbolic point, which are the separatrices. But from those separatrices, it can be reached. And the proof is going to be pretty much a proof by picture, but one thing we need is we look at something which, it's basically a certain matrix J applied to our Hessian U, and it's sort of the first column multiplied by -1 and shifted to the second column. And you do notice this has still the same determinant as the Hessian, and you further notice that the trace of this is going to be XU0. And we can now use the eigenvalues of this. And the eigenvalues are simply lambda1 and, or we call them lambda1 and lambda2. And what now happens, because of the trace being equal to 1, subject to that choice, which can be achieved, there are exactly 3 situations which can happen for those eigenvalues. They can be complex conjugate, in which case their real part has to be equal to 1/2, because they need to add up to 1. They can be real, in which case they're going to be the same distance away from 1/2. And we distinguish 2 cases, either where both of them are positive or where one of them is negative. And what this corresponds to is that if this is the case of your eigenvalues, then your characteristic point has like spirals coming into the characteristic point. If they're real but positive, then this is what is in the dynamical system terminology called a node. And this, so this is now a hyperbolic characteristic point, whereas those 2 cases were elliptic characteristic points. Then you have this like sort of saddle-like feature. And what you can show is that this function is going to roughly behave as 2/s, which you can now put into a black box, which tells you that your stochastic process is never going to hit this point. And similarly here, you can show that this function is going to behave roughly like 1/λIs, provided you are sort of on the characteristic line, which corresponds to the corresponding eigenvalue. And now the crucial thing is that 1/λI in this setting is always going to be positive and strictly bigger than 1. Whereas here, in one case, it's negative, and in the other case, it's strictly less than 1. So in fact, in both cases, it's going to be strictly less than 1. And there is exactly a changeover at this, or phase transition at this 1, where certain associated stochastic processes hits the origin or it doesn't hit. So it's very interesting that this changeover which is happening here, which changes you from an elliptic characteristic point to an hyperbolic characteristic point, exactly on the stochastic side corresponds to a certain Bessel process, either hitting its origin or not hitting the origin. And this is where I would like to stop. Thank you very much.
Thank you very much.